In this video, we will discuss the first types of chemical intermediate, the carbocations. And we'll also go over the factors that can affect the stability of carbocation intermediates. So carbocations are basically chemical intermediates that are produced from the hydrolytic cleavage when the carbon is bonded to a more electronegative atom. For an example, down below, we have a bromine is bonding to a carbon, and because bromine is more electronegative, it can break up and taking the electron away from it. So basically, the step we've seen right here is something that we refer to as the loss of the leaving group. So this is just an example on how a carbocation intermediate will get produced. And the product following this step would then be the formation of the carbocation. So in this case right here, as this bromine or this leaving group or any of the other types of leaving group is breaking up and taking the electron away from it, it is essentially taking one electron from this carbon. Therefore, this carbon will change from neutral to becoming positive. And therefore, we call this a carbocation. And the bromines or any other types of leaving group, as it breaks up, taking the electron with it, it will now becoming negative. And carbocation can be further classified as primary, secondary, or tertiary based on the degree of their substitution. So here is a methyl cation, which is connected to all hydrogen, and then there are no other alkyl or carbon group. Versus a primary carbocation is when we have a carbon here connected to one other carbon group. And a secondary carbocation is then connected to two other carbon group. And similarly, with the tertiary, that is when they connected to up to three other carbon group. And down below are also some special types of carbocation. For example, this one is considered or is referred to as an allylic carbocation. And the reason why is because the cation is located at the allylic carbon. And here is the benzylic carbocation. And again, because this carbon right here is called the benzylic carbon. So when we have a cation located on this carbon, it is called the benzylic carbocation. And then for the structure of all types of carbocation, then all carbocations have the carbon basically have sp2 hybridization. So basically this tells us that there is an empty orbital in here, and in this orbital, this is where the cation is actually located on. And this is actually quite important for us to actually see and be able to recognize that the hybridization of the carbocation carbon is sp2. And because this p orbital right here is empty, therefore it becomes a great electron acceptor. And in chemical reaction, electron can then be donated to this orbital right here to form a bond to this carbon. And it happens through this p orbital right here. And when it comes down to different types of stability of the different types of carbocation, it is then as follows. The more substituted the carbocation, then the more stable they would be. So what this means would then be the following. Methyl cation or carbocations would then be less stable, much less stable than the primary carbocation. And primary is then less stable than secondary. And secondary is then less stable than tertiary. And now, where do the allylic and benzylic fit in on this strand? Then here is the answer. The allylic is more stable than the tertiary carbocation. And then lastly, the benzylic carbocation. So these are basically how all of the carbocations are ranked in order of stability. This would be more stable over here. And we will discuss why we have this strand in a little bit. So now, let's now go over the different factors that can affect the stability of the carbocation. So there are several factors. First one is the inductive effect. So the inductive effect refers to the donation of electron density along the sigma bond on the carbon due to the low electronegativity on the carbon. So let's say here we have a carbocation, and now this is bonded to all the carbon group because all the carbon have low electronegativity. And when this carbon right here positive, this carbon can attract electrons from this carbon-carbon bond to this cation right here in the middle. And because the carbon have low electronegativity, it tends to have the tendency of donating electron in to stabilize this carbocation. So this is the inductive effect. So with this being said, the more alkyl group that is connected to a carbocation, then the more this carbocation right here will then be stabilized due to the electron donating effects from the different alkyl group. And this is why that we have the tertiary carbocation being more stable than secondary and then primary and so on. So that is the inductive effects. And the second effects is called the hyperconjugation effects. And this hyperconjugation effects right here refer to a weak overlapping of sigma bonding orbital on the nearby CH bond with the empty p orbital from the carbon. So here is the structure of the carbocation carbon right here, in which that again we have seen already that it has a charge on this p orbital, and this p orbital right now it is perpendicular to this other bond that we see here. So when we have nearby methyl group in here, for example this CH3 group, and so in here are electron between this carbon and this hydrogen to make up this sigma bond, and we can see that there's a 3 of this CH bond, so there's basically 3 bond group in here. And due to the rotation of this carbon-carbon bond, it can rotate around, and basically there is at one point, basically what happened is that we see that this orbital right here, this sigma orbital, or this that make up this sigma bond between this carbon and this hydrogen, can come quite close to this p orbital, and because this p orbital right here is electron deficient, and this electron it can rotate, but then at one point it might come very close to this p orbital. So there is a tendency where this can donate electron into this p orbital right here, and that helps stabilize this p orbital. So this is then known as the hyperconjugation effects. Now we call this hyper because it actually doesn't really do it, but then they have the tendency to donate electron in to help stabilize the p orbital on this carbon that is very much electron deficient. And so again, this is the hyperconjugation effects. So as we can imagine that the more methyl group that this carbon is connected to instead of hydrogen over here, then we can also have the hyperconjugation effects where the CH bond can again donate electron in because again due to rotation they can come quite close with each other. So this is the hyperconjugation effects, and that helps stabilize the carbocation. And this is the same explanation again why we see the tertiary carbocation that have a lot more of this CH bond. They would then benefit from this hyperconjugation effects and therefore becoming more stable. And now, the next effect that can also stabilize the carbocation is clearly resonance. And this is something we have learned before already as we learn how to draw resonance. So resonance has a huge effect on the stability of the carbocation. Carbocations that can form resonance are especially stable. So now let's discuss the resonance that are produced in the allylic and benzylic carbocation. So in the allylic carbocation, for example, here it is. We can then see that we can draw resonance with this electron move over, and we are now producing the other resonance structure over here. So what this allowed us to do is shifting the location of the cation from this carbon to the other carbon. So this helps distribute this charge on this species, and therefore it becomes more stable. So we can see that we can draw the resonance hybrid in which that we can have the following. And now we can see this become partially positive, this become partially positive. So the positive charge can locate on this carbon or the carbon over here. But it very much is distributed and therefore it's more stable. And similarly with the benzylic carbocation, that can also get stabilized by resonance as well. For example, here is how that can be done. So here is a benzylic carbocation, and as we can see, this part of charge right here can attract the electron from the ring over to produce this resonance structure. And this can further form more resonance structure. And this can further form resonance structure, one more resonance structure. And this can do this again, which then go back to the previous structure that we had from the beginning. So we can see there's up to 4 resonance structure in the case of a benzylic carbocation, versus in the allylic we can produce 2 resonance structure. So therefore the benzylic carbocation tend to be more stable because they're able to produce more resonance structure. So in summary, in terms of stability, the benzylic carbocation will then be much more stable than the allylic, and that is then more stable than the tertiary, and then secondary and primary carbocation. Now, so when it comes down to the benzylic and the allylic carbocation, this can further have substitution on them as well. So the more substituted they are, the more stable they would be. For an example, if we were to have a benzylic carbocation the tertiary, this would then be more stable compared to a less substituted benzylic carbocation, that is then primary. So this is benzylic and primary, versus this is benzylic and tertiary. So the more substituted they are, then the more stable that they will be. So that also applies to benzylic and the allylic carbocations.